Welcome, everyone. For today's prep, I want to look at derivatives of parametric curves. And this is one of our main gadgets that we use in calculus. So if we're kind of looking at these new types of equations and curves, it'd be nice to know how to calculate our standard derivative. And we can. So let's look at how to do this. And I have the formula for our first derivative here. We're not going to look at it, but you can also calculate the second derivative of if you have a system of parametric equations. We're primarily going to be looking at the first derivative, though. So what does this say? So it says the derivative dy dx is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. So remember, when we're talking about a system of parametric equations, we have one formula for x, and then we have a separate formula for y. So x is written as a function of time, and y is written as a separate function of time. All right, so there's a whole lot of derivatives going on here. And it's helpful just to keep in mind what all these different derivatives is. So first of all, what about the main derivative? This is the star of the show here, dy dx. So this is what we're seeing how to calculate. This is the same derivative that we saw all the way back in Calc 1. So this is dy dx is geometric in nature. So if you remember back, all the way back, probably one of the first things we did, the derivative dy dx, it's geometric in nature, and what it calculates is the slope of the tangent line. That was kind of one of the main applications, initial applications that we saw. We could use the derivative to kind of give us this geometric tool that we're interested in, slope of the tangent line. Now, what about these other derivatives? So we've got this derivative dy dt for our y equation, and we've got this derivative dx dt for our x equation. Now, these are fundamentally different derivatives. So dy dt and dx dt, you can think of these are more like velocity. So we're thinking of our function y as y as a function of t, and x as a function of t. So these are giving us, if we remember, our x and y equations are describing the location of a particle that's moving around the plane. That's kind of how we want to think of it. We have our xy plane, and those two equations are describing where our particle is. Well, dy dt is measuring how fast our particle is moving in the y direction, and dx dt is measuring how fast our particle is moving in the x direction. So these are the rates of change in the x and y directions. So what we're doing is we're using how fast our particle is moving in the y direction, dividing that by how fast our particle is moving in the x direction, and doing that gives us this more geometric derivative, dy dx, which is telling us essentially the slope of the tangent line to our curve. And there we go. So same thing, when we talk about the second derivative of y with respect to x, this is also a more geometric type derivative, gives us information about where our curve is, say, concave up and concave down. Now, we do have one requirement here, and that is the x derivative can't be 0, because then we run into problems where we'd have a vertical tangent. And we know, or maybe we forgot, and reminding you, remember when we did those things where we had, back in Calc 1, where we would have a graph, and we'd find those different places where our graph is non-differentiable, so we'd have like the cusps like that, but one of the other ones is where we have a vertical tangent line. So what's happening at that vertical tangent line is the change in our x direction is, well, it's 0. So we end up with a vertical tangent line. All right. So let's try it out. So let's start it with an easy one. So we've got in example 1, we've got our system of parametric equations here. So we've got our x equation, which is equal to t squared plus t, and then we've got our y equation, which is t cubed minus 3t, and we want to calculate the derivative dy dx. So together, these two equations, our x equation and our y equation, together give us our parametric curve. All right, so let's find the derivative dy dx. And so this derivative is our y derivative with respect to t. So we're going to differentiate this equation. And then we'll differentiate our x equation and just put them in this formula. So what's our y derivative? Well, just some basic power rule here. So 3t cubed, or 3t squared for the first term, minus 3 for that second term. So that's the derivative of y. And then we're going to divide that by our derivative of x. So 2t plus 1. And that's it. So notice, back in Calc 1, again, we're used to calculating this derivative dy dx, and then we have a formula in terms of x. Well, now we have a kind of a different type of equation system here. So rather than getting a function of x, what we're doing is we're getting a function of time. So we're ending up here with a function of time. And that makes sense because our curve is being described as a function of time. So the way you can interpret this is if you want to know the geometric slope at a particular moment in time, you can just plug in the t value that you're interested in. So this is telling us our slope at time t. So if I wanted to know the slope of the curve when when our particle starts moving, so at time t equals 0, well, I just plug t equals 0 into this formula, and that would tell me the slope of the curve at that particular point. All right, so let's try an example where we get a little bit more specific, where we actually try to figure out the slope at a particular point. So let's look at example 2. And this is the same system of equations here. So it's the same parametric curve, but now we're going to use this derivative that we just calculated, and we're going to try to find the equation of the tangent line at a particular point. All right. So for a tangent line, what do we need? So let's think back. What do we need when we talk about a tangent line? Well, there's 3 things. We need to know the x-coordinate of our point. We need to know the y-coordinate of our point. And then we need to know our slope. All right. So in this case, sometimes we might have to find the x value. Sometimes we might have to find the y value. In this case, though, we're given the point. We're given where, we're essentially where our particle is. So the x-coordinate here is 6. The y-coordinate is 2. So we want to get the slope. And to do that, we're going to use our derivative. But when we find the slope, we have to evaluate our derivative. Now, normally, when we're finding slope, we just plug in the x value, and that's it. Now, if we go back up to our slope formula, that's what this derivative is. The slope formula here is a function of t. So we need a t value to plug into this. So what we really need, before we can actually calculate the slope at this particular point, we need to know when are we actually at this point. So our first step here, well, before we can actually start finding our tangent line is we really need to find the time. We need to find the t-value when we're at this point. So how do we do that? Well, we know two things. We know our x-coordinate is 6, so we could set either our x equation equal to 6, so 6 is equal to t squared plus t, and we know another thing. We know our y value. So we know our y value must be 2, so we could set our y equation equal to 2. So we end up with two equations that we could solve for t. And whichever one you pick, start with the easier one. So this one's got a cube term in it. This one, the biggest power is squared. So I think this one's going to be the easier one. So we're gonna start with this one. And we're going to solve this for t. So let's move that 6 to the other side. So that'll give us the equation t squared plus t minus 6 is equal to 0. This factors into t plus 3. And I know I'm guilty of it. My t's really start to look like plus signs. So be careful. But this factors nicely. So 3 times negative 2 is negative 6. 3 plus negative 2 is positive 1. So this factors. And what this tells us is we actually get two different t values when our particle has an x value of 6. So from this one, we get t is equal to negative 3. So at time negative 3, our particle has an x-coordinate of 6. And when time is equal to 2, our x-coordinate is 6. So it looks like we have two different times. Well, so these are the only two different times when our x-coordinate is 6. So the thing is we need both of these equations to be satisfied. So not only does our x-coordinate have to be equal to 6, our y-coordinate has to be equal to 2. So that one also has to be satisfied. So we need to check. We need to check if the other equation is satisfied. So it is possible where, as we can see, we have the graph of this parametric curve all nice and plotted out here looking sharp. And with parametric curves, you can have an intersection point where the curve actually crosses over itself. So it is possible you can go through the same geometric point at two different times. That is a possibility. Now, we need to see which of these time values, or maybe both of them, satisfy this other equation. So let's plug both of those in. So we're going to take each of these, and we're going to throw those into our y equation. So when we plug t equals negative 3 in, we end up with the equation 2 is equal to negative 3 cubed minus 3 times negative 3, which, if we do the arithmetic, what is this? Negative 27 plus 9, which is not true. So 2 does not equal negative 27 plus 9. Now what about the other one? Let's take t equals 2, plug that in to our equation, and when we do that, we end up with 2 is equal to 2 cubed minus 3 times 2, and that checks out. 2 definitely is equal to 8 minus 6. So this one, check. So that tells us we've got a winner. T equals 2 is the time that we were looking for. So we know this point 6, 2, let's find it on our curve. So here it is. So this is where our particle is, and we know the time that we're actually here. So our particle is at this point when time is equal to 2. All right, so we've checked it that the other equation is satisfied. So we know for certain that we are actually here. So it's kind of looks like it's plotted. Probably if we kept drawing the curve here, you would see the other point where, or potentially the other point when the x-coordinate is -3, or when time is -3. So probably somewhere down here. All right. So now that we know the time that we're looking for, we can plug this t-value. If we go back, we can plug the t-value into our derivative. And this will give us the slope of our tangent line at that particular point. So we can plug in our t-value. We're going to evaluate our derivative when t is equal to 2. So we can go back up, take this nice sparkly formula that we calculated, and plug in 2 for t. Isn't that a song? I feel like that's a song. All right, so we plug it in. Let's simplify it. So we end up with 4 times 3, which is 12, minus 3. So we end up with 9 on the top. And then in the denominator, we have 4 plus 1, which is 5. So our slope of our tangent line is 9/5. All right, so we're good. We've evaluated our derivative, so now we have our slope. So we have all the ingredients now. So we've got our x-coordinate is 6, we've got our y-coordinate is 2, and we've got the slope of our tangent line is 9/5. So now we're ready to do our line equation. Use the point slope formula to get our tangent line. And if we remember, point slope formula is y minus the y-coordinate is equal to m times x minus the x-coordinate. So we plug in our pieces. The y-coordinate is 2, the slope is 9/5, and the x-coordinate is 6. So this is the slope of our tangent line. All nice. And if we remember, we can always draw in what the tangent line looks like. So it gives us a good approximation for our curve at that particular point. So there's our tangent line. All right. So in class, we'll get a little bit more practice with doing some calculus with these parametric curves. So we'll see you then. Bye-bye.